Hi everyone, in this video we'll talk about the binomial distribution, our first of the discrete distributions. So we'll start by actually introducing a slightly different distribution, the Bernoulli distribution. We'll then extend the Bernoulli to build up or create the binomial distribution. We'll give a definition and some properties of it, and then we'll talk about how to find binomial probabilities. So let's start by defining the Bernoulli distribution. We say that a random variable y has a Bernoulli distribution if the probability that y is equal to 1 is equal to p, and the probability that y is equal to 0 is 1 minus p for all p between 0 and 1. So essentially with a Bernoulli distribution, there are only two possible outcomes, y can equal 0 or y can equal 1. Examples, things like a single coin flip, whether it's heads or tails, single random blood donor, whether they're O positive or not, etc. Anything with a binary outcome, one trial can be modeled using this Bernoulli distribution. So suppose that a national pollster wants to estimate the president's approval rating. We'll let P represent the unknown proportion of all U.S. adults who approve of the president. Suppose a random sample of 100 adults is taken. Each person in the sample will be asked the following question. Do you agree or disagree with the president's handling of his job? We'll make an assumption here, and we'll assume that the voters are independent and identically distributed, or IID, meaning that no voter is influencing another, and they all have the same baseline probability of approval. So first, let's identify the Bernoulli random variable and then find an expression for the probability the entire sample approves. So the Bernoulli random variable here is the approval rating. For each person surveyed, we'll let y equal 1 if the person approves and y equals 0 if the person does not approve or disapproves. So then we say that y is distributed Bernoulli with probability p. What we'd like to know, or what this distribution depends on, is that underlying probability p. So by the multiplication rule, the probability that all members of a sample of size n approve is p times p times p times p, all the way out, p raised to the n power. How does this probability that they all approve change depending on p? Well, we have a fairly large sample here. We have a sample of 100, so this probability changes pretty quickly. For small probabilities p, it's very unlikely that 100 people would approve, almost impossible. But as the approval rating approaches 1, the probability that all voters would approve becomes even higher and higher. So let's find an expression now for the probability that instead of all 100 approve, maybe just y voters approve. So we'll assume that all n voters are again independent. Let's build up what this might look like. Starting with the y approvals using the multiplication rule, the probability that y voters would all approve is p raised to the y. For this disapprovals, the same idea. We'll take 1 minus p, because that's the probability that they disapprove. In a sample of size n, if there are y approvals, then there must be n minus y disapprovals. Now, how many ways can that occur? It could be that the first y that are asked in a row might all approve. It could be that the first person disapproves, the next y people approve. The y's could even be more interspersed. So how many ways can we choose? Well, we've got a combination. The order doesn't necessarily matter. We just need to know how many ways to shuffle this. So n choose y is the number of ways this can occur. When you multiply all of these together, you get the binomial distribution. So a random variable y is said to have a binomial distribution with two parameters, or two numbers that control the distribution, n and p, if the probability that y is equal to y is n choose y times p of y, or times p raised to the y, times 1 minus p raised to the n minus y. The number of approvals, or the number of successes, can go from 0, 1, 2, all the way up to n. So we say that y is distributed binomial with np. The shape and the skew of the binomial distribution, so what this binomial distribution looks like, changes depending on those two parameters, changes depending on the number of trials n, and the probability of success p. So what you're seeing here is actually a binomial distribution with n different trials, so a sample of size n, if you will. Probability of success, 50%, 0.5. The most likely outcome, the outcome with the most probability, is here in the center, y equal to 5. Y equal 4 and y equal 6 are pretty likely as well. Probabilities are fairly low the farther you get from the middle of that distribution. Now, as we change the probability of success p, and as we change the number of trials, the distribution moves around a little bit. So for example, going from p of 0.5 to p equal 0.8 shifts the distribution to the right. We start assigning more probability to higher values, less probability to lower values of y. The more samples we take, the more outcomes we can observe, so we start having more outcomes, if you will, more constricted plots. We go from 10 to 50, same shape, however the distribution seems to narrow. 10 to 50, same shape, the distribution does seem to narrow a bit. So let's take a look at an example of finding probabilities with a binomial distribution. Suppose a multiple choice exam has 10 questions with 4 choices for each question. If the student plans to guess on each question from the available choices, what is the chance that they will get exactly 2 questions right? So we're going to let y be distributed binomial. N is the number of questions, so there are 10 questions. P is the probability of guessing correctly on any individual question, so P is 1/4. So we'll let the probability then that y equal 2 be 10, choose 2, times 1/4 raised to the second power, times 1 minus 1/4 raised to the 10 minus 2 power. So the probability that y is equal to 2 then becomes 0.28, or there's a 28% chance. If we'd like to calculate this probability using, say, r, instead of calculating it by hand, we can do so with a function called the d-binom function. So the binom stands for the binomial distribution. The d stands for the distribution. So we're calculating probabilities related to a binomial. Here we input our observed value, or our desired observed value. Here that's 2, so that is the x argument. The size argument is n, how many trials we have, so in this case 10. The prob argument is the probability of success, in this case 0.25. When we run this in R, we get back the value that we calculated by hand. In fact, here is a plot of this distribution, so you can see what this would look like. 2 is in fact the most likely outcome. Y being 3 is fairly likely, so it's getting only 1 question right. So if this multiple choice exam has 10 questions, again 4 choices for each question, what's the chance that the student will get 2 or fewer questions correct? So there's a few ways that we could approach this. We could approach this by adding up all of the outcomes that are less than 2. So the probability that y is less than 2 is the probability that y is equal to 0, plus the probability that y is equal to 1, plus the probability that y is equal to 2. So we'll calculate all 3 of those binomial probabilities. It'll look a little bit like this. There they all are. We add it together. There is a 53% chance, roughly 0.5256, that y is less than or equal to 2. We can also calculate multiple probabilities at a time in R instead of doing it by hand if we choose. We do this using a colon. So what that colon does is define sequences increasing by 1. So if we write in R 0:2, that returns the integers 0, 1, and 2. So using the d-binom argument in this way, we'll calculate all of those individual probabilities. We can add them up to find the probability that y is less than or equal to 2. Or if we'd like to calculate what are called cumulative probabilities, so probabilities up to a particular point, instead of using the d-binom function, we can use a function called p-binom. So here we're using P binom. Q stands for quantile, so we want probability up to 2. Size 10, probability 0.25. And we get the same answer that we found by hand. Now, what's the chance that the student will get more than 2 questions right? Again, a few ways to approach this. We can certainly do this the hard way. So the probability of getting more than 2 questions right is the same as the probability of getting exactly 3 or more. So we could find the probability of y equal 3 plus the probability of y equals 4 plus the probability of y equals 5 and so on all the way up to y equals 10. That will take some time. The easier way here would be to use the complement rule. So the probability of getting more than 2 questions correct is the same as 1 minus the probability of getting 2 or fewer correct, so 0.47. Now, it turns out that there are a few more binom functions in R that we might want to use, and let's go through what each of them are. So the D binom function we've already seen calculates distributions or probabilities. The P binom function calculates cumulative probability up to a particular point. The Q binom function isn't one that we'll use all that often. This one calculates quantiles, so it finds a value that caps a particular cumulative probability. And then finally, the R binom function generates random binomial variables. So let's take a look at an example. Letter et al. In a 2002 paper estimated that 12% of booked passengers do not show up to the gate due to cancellations or no-shows. So let's say that an airline plans to sell 110 tickets for a flight that seats only 100 passengers. You've probably seen this happen at the airport before. The flight attendants or the people at the gate, that's the right word, the gate attendants tell you that the flight is overbooked. They're asking for volunteers to take another flight. What's the probability in this situation that might happen? Well, we can use the P binom function to help us out. Before we continue, think about how you might write this. So try writing this on your own or conceptualizing what this probability is going to look like on your own. All right, let's work it out. So we're going to let y be the number of passengers that arrive for a flight, assuming that the passengers are all independent. This might be a big assumption, but we'll go with it. There's no groups. They're all single travelers, unrelated. Then y is distributed binomial with n equal to 110, p, probability that a passenger will show up for the flight, 0.88. The airline overbooked and will run out of seats if the number of passengers who show up, y, is greater than 100. So using r, the probability that y is less than or equal to 100 is about 86%, 0.8633. So then the probability that y is greater than 100, so starting at passenger number 101, we've overbooked the flight. Well, it looks like this would happen about 13.5% of the time using the complement rule and the binomial distribution. Let's take a look at another example. So studies have shown that 30% of all people afflicted by some serious illness recover. A drug company has developed a new medication for this illness. 10 people who have it are selected at random and receive the medication. 9 of the 10 do recover. Suppose the medication is actually ineffective. What's the probability that this would occur? What is the probability that at least 9 of 10 people receiving the medication would recover? So we'll let y be the number of people who recover from the illness. Y is a binomial distribution. There are 10 people who have the illness that we're studying. We're assuming that the medication doesn't work, which would mean that the probability of recovery is 0.3. So the probability that y is at least 9 is the probability that y is equal to 9 plus the probability that y is equal to 10. Plugging those into the binomial distribution, we can go ahead and calculate this out. I do want to point here in the second one that there is a LaTeX bracket that is missing, so this should be a 10 in the superscript, not 1 and a 0 down there, so apologies for that typo. We get a probability that y is greater than or equal to 9. That is incredibly small, 0.0001. So do we think that the medication is effective based on this? Well, if the medication isn't helping people recover, then the recovery rate would only be 30%, and it would be very unlikely to observe 9 out of 10 recovering. Maybe it's more reasonable to conclude that the medication has helped. This would certainly be a more likely result if the probability of success P were in fact higher. All right, so let's talk about some properties of the binomial distribution, specifically the expected value and the variance. So suppose that y is distributed binomial with parameters n, p. The expected value of y, the expected number of successes, is the number of trials n times the probability of success p. The variance of y is n times p times 1 minus p. So let's find the expected value and variance for the number of passengers who will show up for the flight. On average, how many empty seats would we expect? So y is distributed binomial. We have 110 seats that we are planning to sell, or tickets that we're planning to sell, I should say. Probability that someone will show up to use that ticket is 88%. So our expected value is n times p, or 110 times 88%, or 96.8. So we expect about 97 of the passengers to show up. That means that on average, if 97 passengers do show up, we can expect about 3 seats to be empty. The variance here is n times p times 1 minus p, or 110 times 0.88 times 1 minus 0.88, variance of about 11.6. So we will stop here. In the next video, we'll introduce another discrete distribution, the geometric distribution. See you then.